Welcome back to another video, and today we're going to be learning about Euler's method, or how to approximate a value more accurately than linearization. So first we can start off by stating that y equals f of x, right? And then we know the derivative of y is just dy over dx. And let's just draw on a little tangent line here where this is dx and then this is dy. Okay, so for any equation, no matter what, delta x is equal to dx. The change in x never changes. Only the y value gets approximated. So what we can say is the change in y is approximately dy, because it's not exactly like delta x, which is equal to f prime of x times dx, which is basically equal to dy over dx times delta x. We can simplify that by saying y of x plus delta x is equal to y of x plus dy, which gives us our formula for Euler's method. Y of x plus delta x is equal to y of x plus y prime delta x. Once we have this method, we can start doing questions like this. So let's first read the question. If f of x is a particular solution to this differential equation, x plus y, and we're given a point y of 1 equals 0, how will we use Euler's method starting at x equals 1 with the step size of 0.1, basically saying delta x equals 0.1 to get to 1.3. So immediately what I'm saying is I will need 3 steps. 1.1, 1.2, and finally 1.3. And since f of x is greater than 0, we can use that information later to see if it's an overestimate or an underestimate. So first, we have to start with our point, 1, 0. And using our equation, y of 1 plus 0.1 right here, we can approximate this. So it would be y of 1 plus the derivative of 1 times our delta x, which is 0.1. Since we're given this point, we can start it off. So y of 1 is 0.1, or y of 1 is 0 plus 1 plus 0 times 0.1, which is equal to 0.1. So now that we have this, we have an approximate value for 1.1. So if we kind of look at this graph, we can see what it's getting at. So this is our first point, and now once we're at this point, we're going to use that to readjust to a new tangent. So instead of being over here when we had a of 5 and way off, if we keep readjusting every interval or delta x, we would get close enough eventually. So now we have our second point, right? So then we'll do y of 1.1 plus our delta x, which is 0.1. That's y of 1.1 plus y prime of 1.1 times 0.1. And we know that y of 1.1 is 0.1 plus 1.1 plus 0.1, or that value plus delta x times delta x. And this is equal to 0.22. So we can say that our second point is this, and now we'll correct ourselves or readjust ourselves again. So y of 1.2, this will be our last step to get to 1.3, and then we have y of 1.2 times 0.1, which is equal to, we said this was equal to 0.22 plus 1.2, which is our value we're trying to find, plus that value times 0.1 is equal to 0.362. So that means we can approximately say that f of 1.3 is approximately equal to 0.362. And now we can finally find if it's an underestimate or an overestimate. And to do that, we'd have to find if it's concave down or if the function is concave up. So I'm given my first derivative, and then the derivative of that is 1 plus dy over dx, which is equal to 1 plus x plus y, since dy over dx is x plus y. And since x is always greater than 0, and we're given y is always greater than 0, we know that this is always positive. And when a function is always positive or concave up, it means that our approximation will be an underestimate. See here, if we keep readjusting ourselves, we're never going to cross it. So let's do another example with a question like this. So pause the video and try to see if you can do it yourselves, and if not, we'll get started. So we're given our point initially, 3, 1, and 2 total increments to estimate 2.4 from 3. So that means my delta x will be negative 0.3, since 3 minus 2.4 over 2 total increments is negative, or 2.4 minus 3 over 2 is negative 0.3. So we're going to start with our point y of 3 equals 1, and then we're going to do our first tangent. So we have our y of 3 value plus our differential equation, which is 2y. So 2 times the value of y, which is 1, times our delta x, which is 0.4. So now we have another point, 2.7, 0.4. And then we're going to do it again. So we'll use our point y of 2.7 plus negative our delta x to negative 0.3 equals our y value plus 2 times, or our equation times our y value times negative 0.3, which is equal to 0.16. So we can say that f of 2.4 is approximately 0.16.